Welcome back to our study of differential equations. And as we discussed before, this is where the action is in calculus development and research. We're going to use Scientists use differential equations to model all kinds of physical systems. And from the modeling then of differential equations, they're interested in finding the function itself. So that's really how things are done. I know in calculus books you're saying, here's the equation, here's the function, now do calculus. And more realistically, you're given a differential equation, and you have to do integration in order to find the function. Okay, what I think is interesting to do is to use the solution of differential equations in order to derive some of the formulas you've used in other classes. And one of my favorites to work with is to derive some of the projectile motion equations from physics. Okay, and you do a lot of these. You fire up a cannonball in the air and you calculate what its speed and velocity is, what the height of the projectile would be, and maybe how much time it was in the air, when did it hit its maximum, and things like that. And you do that all from the particle motion problem. So I want to derive those here. So it all starts off with this simple equation right here. I say in a gravitational field, the change in velocity with respect to time is equal to the gravitational acceleration. It is a constant. It's equal to a constant, and if I'm using the metric system, I might say that's 9.8 meters per second. And I could call this in a negative direction. I guess I could call it negative 9.8 meters per second if I wanted velocity going down as being negative and going up as being positive. I could call this negative. Or if I used a British units, I could say that's 32 feet per second squared. Well, this is squared, second squared. Okay, now when I solve a differential equation, I have a differential equation, but in order to come up with a unique solution, what else do I need? I need a point on the solution curve. What's the solution? I'm trying to find what v is. I need a point on the velocity curve. So I kind of make it up. I say, well, v at time 0 is equal to something, and I'll call it v0. I don't know what it is, but it's some constant v0. Now, with this in mind, a differential equation and a point, I can solve this. Okay, how do I do that? First thing I do is I separate. I say dv is equal to a dt. Not much in the way of separation there. Let's make sure I'm recording. No trouble before. Okay, now I'm going to integrate both sides. Integrate dv, I just get v is equal to at plus c. Okay, solve for c using my point on the curve. Okay, so v at 0 is equal to v0. It's equal to a times t, and t is just 0 plus c. Well, that's 0. So c is equal to v0, and this leaves my result to be, voila, velocity, and I could say, hey, that's velocity as a function of time is equal to a times time, the acceleration due to gravity times time plus the initial velocity. Okay, so you use that to calculate, when, for instance, when is this particle not moving? When is velocity equal to 0? Okay, let's continue on, because there's another, how do you get the equation for displacement? Where is the particle? Let's do that next. Okay, here we'll start with this equation. This is where we left off, right? Let's change colors. Let's turn this into another. Remember, we know what is velocity? Well, velocity is just the change in displacement with respect to time. So I'll rewrite this and put a differential equation in it. Okay, so here's another differential equation. I need a point on the curve, though, don't I? I need to know, solving this differential equation, I'm finding S. So I need to know a point, and I kind of make it up. Well, S at time 0 is equal to my initial displacement. A lot of times, we say that's equal to 0, but we're not going to do that here. We're going to do it right. Okay, first thing I do is what? Separate variables. ds is equal to a times t plus all times dt. Separate variables, step 1. Second step, let's integrate. Integrate the left side, I get s, or I could write it s as a function of time because the other side is, and I get what? A times t squared over 2. Remember, a is just a constant. V0 is a constant too, plus V0 times time, plus the constant of integration. Plug in my initial condition, and what do I get? Well, S sub 0 is just equals to S0 is equal to A over 2 times 0 squared plus V0 times 0 plus C. These are 0. C is equal to S0. So, grand finale, dump, bump, dump, I get S sub t, displacement is going to be A over 2 t squared plus V0 times t plus S sub 0. And there is the formula you've used before to calculate what? If you know the initial velocity, you know how long this projectile's been traveling, you can then calculate where the projectile is as a function of time. Here you can calculate, so you could basically find where's its maximum. Where is this? If you want S of t to be a maximum, if it's going to be shot up out of a cannon and then come down, you could find out where is, take the derivative of this, set it equal to 0. Guess what? That's where the velocity would be equal to 0. That's when t would be equal to at is equal to minus v0. T is equal to minus v0 over a. So anyway, you work problems like that. The point of this, though, is not to work physics problems. The point of this is to start with a simple model for projectile motion in a constant gravitational field, and to derive from that model, to derive all the equations necessary to solve those physics problems. Okay, the next thing we'll look at is exponential growth. And here we go. Exponential growth. Here I'm going to give you a verbal description of a differential equation. Okay? Exponential growth. Rate of change of a quantity is proportional to the quantity itself. Okay? Turn the model text into a differential equation. Okay, the rate of change of a quantity, well, I'm going to call that dp dt. It's proportional to the quantity itself. Okay, what's the quantity? The quantity is p, so I'm going to say that's equal to r times p. Okay, I kind of paused things and I changed the notation here. So I changed my p's to a's. Oops, because I wanted to be able to derive an equation I think you'll recognize. Now this thing, so I took the verbal description and I turned it into a differential equation. And I want you to see if this makes sense here. I said you need to be able to translate and read differential equations, okay? Just before we even get a solution, let's see if we understand what this means. In this case, this is going to be like money in a bank account, okay? Money in a bank account. Let's get a little drawing here. And when you open a bank account at time equal to 0, you're going to have a beginning amount, and maybe I call that P, my principal amount, okay? I'm going to start at the principal amount, and when I put in a principal amount, that principal is going to be A, and when my rate might be 6%, say I put in $1,000 here, so if I put it in at 6%, $1,000, I'm going to get six. You know, this is going up at say $60 per unit time. Okay. Now, if I now I have more money. As the money grows, the derivative increases. Okay. And then it's going to, you know, every time as A, this is A here. A is a function of time. That's what I'm trying to find. This is time. As A increases, the slope increases, right? Isn't this what this tells me? As A increases, the slope increases as long as R is constant. Okay, so A increases, the slope increases. So I'm getting something that's, as it gets larger, the slope is increasing also. Anyway, so that tells me kind of how to read this thing. Now let's solve this. Let's solve it. Let's just use okay, so again, we'll write this down. dA dt is equal to some proportion of the original amount. And now I'm going to say, well, I need an initial condition. So I'm going to say the amount in my bank account at time 0 is equal to the principal that I put in. Okay? At time 0, the amount, A, in my bank account is equal to the principal, P. All right, so let's solve a differential equation. Remember, R is a constant. So here, the first thing I do is what? You're correct. I separate variables. dA is equal, dA over A is equal to R times dt. And you know, you could bring R constant over to the left side, but keep all the constants on the right side of the equation because this is a simple integral. Next thing I do is I integrate. The integral of 1 over A is just going to be the natural log of A is equal to RT plus C. Okay. This is a very important differential equation to be able to solve, so pay attention here now. Well, I could solve for C now, but I'm not going to. I could. I get the same answer, but the first thing I want to do now is I want to isolate A. And how do I do that? Well, I'm going to take an exponential of both sides. Okay, I'm going to take the inverse of both sides. That is not a negative sign. Don't for a minute think that's a negative sign, okay? Well, e to the natural log of A is just going to be A. This is going to be e to the RT plus C, but let's use a couple properties of exponents. This is also equal to e to the RT times e to the C, right? But e to the C, that's just another constant. Another constant. So we say e to the C is just equal to another big C. Big C, e to the RT. So A is equal to e to the RT. Well, how do I solve for C? How do I solve for C? Well, I use a condition up here, right? And that says A of 0 is equal to P is equal to C e to the R times 0. Well, that's equal to C times e to the 0, but e to the 0 is just 1. So that's equal to C. So C is equal to P, right? And now I think you maybe have used this in calculating interest, maybe in another class. You're going to say A is equal to P E R T. What does that tell me? That tells me if I let my bank account continuously compound at a rate equal to R, and if I started at time equal to 0 with, in fact, I guess I could draw the curve. It's an easier thing. I can talk, But curves and equations are so much more precise. See, that's the beauty of mathematics here. If I start here at P at time equal to 0, if I then after another time t out here, the equation for this is a of t, is just going to be equal to, this equation is going to be p e to the r t. Losing my calibration here. I think you see what I'm trying to do, okay? All right, so that's an important equation to be able to solve. This describes, again, exponential growth. This is exponential growth. I could have easily come up with something where I did what? Exponential decay. I'd say, well, dy dt is equal to minus k times y. Okay, I'm going to do the same kind of solution, and you'd say, well, y is just equal to y0 e to the minus k t. And in this case, my curve, so you could solve this. I didn't show you the steps, and it would come down like this. This would be y of t. This is t. Where does it start? It starts at y0. And it decays. So this is exponential decay. Okay, versus this exponential growth. Okay, so what did we do today? In summary, we used the ability to solve differential equations to derive some of the equations we use in physics, projectile motion problems. Here we've got, and also to derive an equation we use for calculating bank accounts and interest rates. We use the A-PERT equation. So, and we can derive, this is a key thing here. The key thing in this thing, and the key thing where people make mistakes. When I did this, I go to this, and my constant is a multiplicative factor, okay? It is not, notice the c comes in after I integrate. What happens to people is they say, oh, I need a plus c, they do all that. They add a plus c out here in this equation. That's bad news. Anyway, so I'll probably work some of those in class, and I'll remind you where that mistake occurs. Anyway, we're running out of time here. I hope that was helpful. We'll see you soon.